Hey guys, so in this video we're going to look at a slight variation of these collision with motion problems. Now, when you have both collision and motion, or motion and collision, you're going to use both conservation of energy equation and conservation of momentum equation. In the standard problem, something gets hit and the object that gets hit moves. Maybe it goes up a hill and you might want to know how far up the hill does it go, or how much does the spring compress given the initial velocity. In other types of problems, which is what we're going to do now, we're going to work backwards and I will tell you how far the block goes and ask for the initial velocity in the beginning of the problem. So let's check it out. All right, so it says here in some collision motion problems, you're going to be asked to calculate the initial velocity. So the problem works backwards, right? It's basically kind of like forensics. If the block moves this much, how fast must the bullet be moving before it hit the block? Okay, so here I have a 300-gram bullet that strikes a 10-kilogram block that is at rest. So let me draw this real quick. Here's the bullet. I'm going to call it mass 1, and it's 0.3 kilograms, and it's going to strike a 10-kilogram block. So mass 2 is 10 kilograms. The bullet has some sort of initial velocity. The block is initially at rest. Okay, it's on a horizontal surface. The bullet's going to stay inside of the block, so later on the bullet's going to stay inside of the block, and it's going to cause the system to move after, right? It's as if the coefficient of friction between the block and the surface is 0.6, so that's a coefficient of friction between the two. So what I'm going to do is I'm going to draw the floor like this, the surface like this, just to indicate that there's friction, and the block slides a total distance of 35 meters. So after being shot, the block goes from being at rest and then it slides 35 meters. So let's say 35 meters ends right here. So this distance, I'm going to call it delta x, this displacement, is 35 meters. I want to know the speed with which the bullet hit the block. In other words, I want to know the pre-collision speed of the bullet. Okay. Now, if it travels a total distance of 35, it's implying that the final velocity here is 0, that the block stops. Okay. And as always, we're going to use conservation of energy and conservation of momentum. The first thing that happens in this problem is a collision. So from A to B, I have a collision. Therefore, we're going to use the conservation of momentum equation. And from B to C is where the block starts moving and then it stops. So at point C, it stops. And we're going to use the conservation of energy equation here. I want to remind you that before the collision is A, in this case, because it's to the left here. And then after the collision is B. So this is pre-collision. We call B post-collision, and we call C the end where the object stops. So when I wrote here that V final is 0, just to be more specific, this is VC, okay? VC of both the block and the bullet. All right, so let's write these equations from A to B and B to C. From A to B, I have, as it says here, a momentum equation. So I'm going to write M1V1, M2V2, M1V1, M2V2. And this is from A to B. Okay? I'm going to go ahead and write the B to C equation already. Let's pick a different color. From B to C, I have the energy equation. So it's K plus U plus work non-conservative equals K plus U. In this case, we're looking at B, B, C, C. All right, and I want to know the initial velocity of the bullet. Bullet is 1, and before the collision is A. So I want to know V1A, okay? And I really think it helps to know exactly which variable with all the little subscripts and whatnot you want. Once you identify that correctly, you can just look at the equations here and you know exactly what you need, and what you need is this guy right here, okay? So because this is what we're looking for, I'm going to start there. I'm going to start with that equation. Now let's see what I have. I have all the masses. The initial velocity of the second object before the collision, right, is 0. The block doesn't move, so I can scratch this whole thing. And do I have these final velocities? I checked this off, but I actually don't have this. I don't have V1B, I don't have V2B. However, the bullet stays lodged. This is a completely inelastic collision. And even though I don't have these velocities, I do know that at least they are the same, which means I can combine them. So instead of writing V1B and V2B, I'm going to write just VB, and I'm able to combine the masses M1 plus M2 because they're moving together. And then here I have M1 V1A. M1 V1A is what I want, so what I can do is just divide both sides by M1. I'm going to go ahead and remove this M1 here, and we are done with this part of the problem, with this equation here, where as long as I have all these numbers to the right of the equal sign, I'm good. I have everything except VB. I don't have VB. So what do? I go over here, I go to the other equation to find VB. And VB, by the way, if you look here, you should know that VB will show up inside of KB. Kinetic energy is half mv squared, and I'm looking for the B1, so it's going to be here. But you don't necessarily have to look for it before expanding. You can just go ahead and expand it, and it's going to show up. Cool? So even if you're not sure if it's there, sometimes that happens. You expand the whole equation, it's going to show up. So is there kinetic energy at point B? Kinetic energy at point B. Point B is post-collision. Post-collision, you're always going to have kinetic energy. So yes, there's no potential energy at point B because at no moment does this thing either go up a hill or compress as a spring. So no, there's no potential energy in the beginning or in the end. Is there work non-conservative? Work non-conservative is the work done by you. You're not doing anything, you're just watching, so you don't do that. There's no work you. But there is friction. There is work done by friction. Okay? We'll get back to that in a second. And is there kinetic at point C? The answer is no, because at point C you stop. All right? So let's expand this. This is half mvb squared. VB is what I want. And then plus work non-conservative. I'm going to go off to the side here, and I'm going to derive work non-conservative. Okay, so this is sort of to the side. Work non-conservative is just the work done by friction. Remember that the work done by friction is negative FD. Remember that friction is mu normal. And remember that normal in this case here is, because there are no other forces acting on the y-axis, normal equal to mg. So now we're going to work our way back. If normal equal to mg, then friction is mu mg. And if friction is mu mg, then the work done by friction is negative mu mg d, which is also the work done by non-conservative forces. Okay, so you got to do all that. You have to be good at doing that. And this is what goes right here. Negative mu mgd equals 0. I'm solving for VB, so I'm going to move this guy to the other side. And you see that the masses will cancel. Check it out. mgd. The masses cancel. Now, if the masses didn't cancel, it would be important for you to know which mass to use. And in this case, mass would have been m1 plus m2 because the system moves together. The two objects move together. But you could screw that up because the masses are going to cancel anyway. So even if you had the wrong number there, you would be fine. VB is what I'm looking for. It's going to be the square root of 2 mu gd. And if I plug in these numbers, mu is 0.6, gravity is 9.8, and the distance d delta x, doesn't matter, is 35. If you take the square root of all this, you get, I have it here, 20.3 as the velocity. Now 20.3 is the VB, which is the post-collision velocity of both of these things. But that's not what we want. What we want is the initial velocity. So what I got to do is plug this number into here. Okay, but now we're basically done. Just got to plug it in. So V1A equals 20.3. The masses are 0.3 and 10. And this is 0.3. And let me see, do I have this here? 10.3, 20.3.3, yep, I got it. So this is going to be 697 meters per second, and this is the final answer, okay? The initial velocity of the bullet is 697. So we were able to work backwards to get the velocity. It's very simple. It's very, very similar to what we did before. We're just asking for a different variable. The process is pretty much still the same, which is you draw the collision. I like to draw this to help organize our thoughts. Then you write the two equations and you plug stuff in. Okay? So that's it. Let me know if you have any questions.